Suppose that we construct a sequence of probabilities of the number of heads x in n tosses. So if I ask you what's the probability that x is equal to 2, the number of heads, you get 2 heads in 5 tosses of coin. You know to use the binomial. So we evaluate the binomial at that small sample size. And we compare the probability function for that binomial on a sample of size 5 with a normal distribution. So we draw the CDF, the cumulative density function, for a normal, and then we draw the cumulative density function for a binomial of size 5, sample size 5. And then we compare, we see how well the two CDFs line up. They're going to be quite different. You would expect that, because with those small samples, there's a big difference between the binomial and the normal. So then we go a little further and we say, well, now let's count up. Let's look at the distribution of the number of heads in 100 tosses of the coin. And we construct the theoretical cumulative density function for a binomial random variable where we have 100 repetitions. And we look to see how that compares with the normal. And we're a lot closer than when we had a sample of size 5, but still doesn't look too great. And then we do it again, this time for a sample of size 10,000. And we construct the binomial CDF for a sample of size 10,000, and we compare what that function looks like next to the normal. And boy, now they're really getting close. In fact, if you pick a point on the domain and you map it to the function, and you drew a little circle around the point on the normal, probably at a sample size of 10,000, the point on the binomial CDF would be inside that little circle. But you guys are really playing unfair, and you said, well, that circle's still too big, Dr. Buck. I'm going to make it really small. And I said, well, okay. In that case, let me make the sample size 1,000,000. And I'm going to write down the binomial CDF for samples of size or repetitions of 1,000,000. Draw it on a piece of graph paper, draw the normal CDF, and now anywhere on the support of those two probability distributions, the difference between the binomial and the normal is minuscule. You can't tell the difference. So as the sample size gets large, the binomial CDF is converging in law to the normal. So we're comparing the sequence of probability functions to a known distribution. And if the sequence is converging to the known distribution, then we say that the sequence is converging in law or in distribution for this particular thing that we had in mind. So, to come back to Wald, likelihood ratio, and Lagrange multiplier, how did those guys know that the limiting distribution was chi-square? Well, it turns out that there is a little summary diagram, which is in the online lecture note, which says that if some statistic based on a sample of size t converges almost surely to a random variable x, then xt converges in probability to some random variable x, the same one. And if that same random variable xt converges to some parametric random variable, then xt converges in distribution to that particular random variable. And also, if xt converges in quadratic mean, then xt must converge in probability, and it must also converge in distribution.
Distribution as law, right?
Yeah, so sometimes you'll see it written as a D or an L, converges in distribution or converges in law. Not in law, it uses the idea of law, but this is conversion of law. So what they needed to do was show that the W statistic, which remember was beta hat minus beta 0, squared converged in quadratic mean on 0 when the null was true. That's easy to do. And knowing that, we can show that the Wald statistic under the null is consistent and therefore converges in law to some known distribution, in this case chi-square. So they knew where they were headed. The tip-off was the sums of squares, and the sums of squares business is common to all three testing systems. So they knew they were headed to chi-square. So they knew that they had to show that their test statistics converged in quadratic mean to a chi-square. Once they could do that, then they knew they were done. So they didn't have to actually do some algebra to show that W had a chi-square distribution. They just needed to show that it was converging in law by working from backwards through the causation.
So likelihood ratio test, there's no sums of squares in it, is it?
Sure. In order to do the likelihood ratio test, you have to have a likelihood function, right?
Yeah.
So the likelihood function that people often choose is normal. And what's up in the exponent of the normal? Sums of squares.